Let's take a look at Analog IO. That is the lesson for this week. Before we do that, we're going to review the sequencers for just a little bit. So on the sequencer lab, I feel that most people get a pretty good idea of how the sequencers work, how they scroll through a file and push a word out to usually an output module. The issue is the problems with the applications. You just see how the sequencer works, or an SQO or an SQI, how the masking works, really understanding how that word works. So a couple things to keep in mind. The position is advanced via the SQO. So when that goes false to true, the position advances. And if we're using an SQI, we need an SQI and we need the SQO, and they have to use the same control, because the SQO is what is advancing, and if they use the same control, then every time the SQO advances, then the SQI will advance as well. So it says the SQI is externally indexed. If you had an SQI and just tried to cycle through it, it wouldn't advance. You need to advance the SQO, and then that control causes the SQI to advance. Okay. We did been doing a lot with data, okay, and there were some questions about just taking a look at the data on SLC 500. That's shown when we look at a word, it's horizontal, versus in the logics here it's vertical, and sometimes that's just a little bit confusing. And it says take a look at data example 1 here, and so I'll just take a look at that real quick. And that says, take a number here and expand it to provide a binary number. And so we did a lot of this to convert it to binary. So we did 1, 2, 3. That's our number. We know that 128 is too big, so it's not going to be here. Everything over here is going to be zeros. It's because 128 is bigger than 123. But we can start adding 64 plus 32 plus 16 plus 8, and that gets us pretty far up there. That gets us up to 120. 4 would put us over. 124 is too high. So then we would go 0 and 1, 1. So we did a lot of conversion here. And you can use your PLC. Like I said, I usually have a tag called math or something, where if I want to put in a number, I can convert back and forth between the binary and the 1, 2, 3. And we'll talk about, why we really want to do that as we get here in our review. Okay, we did some masking. Okay, and so what a mask does is it allows some of the data to pass through and some of the data not to pass through. So the question here is, what is the mask for 16 FFFF, and how to change that to a decimal, double integer, and what we're going to do is we're going to take a look at this again. So I've got another example here. It says, this is a binary mask. So notice that there's 32 spots here. This would be the first part of the word, and that would be the second. And this is the first part, and that's the second. So if you wanted to start down here, I guess, it doesn't matter, because these FFFs, this F is for the first 4 right here, and the next F is for the next 4, and then the next 4 and the next 4, like that. So we went and we learned that this was 1, 1, 1, 1, 1. This would just be all ones. This mask would be right here, whereas this F is the first part of it, and this F is the second half of this double word, okay? So if we're only using an int and not a dint, well then a lot of times we can take the second part of this and we can just mask it off with all zeros. So we could have went 0, 0, 0, 0, and then FFFF. And then that means that we pretty much take out the first part of this word, and we turn it into an int, because we're not going to allow any data to pass through it, even though it does have additional data. If we masked it, it wouldn't be coming through. So hopefully you understand how our masking was working here. You remember in that sequencer one, or the FIFA one, we changed the mask right here at the very end to a 0, so that we wouldn't let any odd numbers to come through. So in that lab, when we were masking, we were only getting even numbers, because any odd number got blocked and got brought down to a 0 right there. So did a little bit of masking, and we're gonna review some more on that as well. So it says how to quickly fill a file with conversion, use binary to get decimal, then type decimal, things like that. So we got one more little example here. And what I've got going there is this. It says how would you quickly fill a mask? So with 1, 3, and 5. So bit, that's my 0 bit. So I guess my 1 bit's here, my 0, 1, 2, 3, 4, 5. So that would be my first one here. And I could do the math on this and say that's a 0, a 2, a 4, an 8, a 16, a 32. Add it up, that's 42. And the next one is 1, 2, and 3 masked. So 0, 1, that's the 0 bit, the 1, 2, 3, and the 4 bit. And if I did the math on this, it would be 16, 8, 4, and 2. Add them up, and I get 30. Okay. So if I really needed to work quickly in throwing masks and throwing numbers and fill up a file with words, it's a pain in the butt to come in here and expand this word and type, a 1 and then click in a 1 and a 1. It's easier just to type in here a 42 or a 30, okay? So for example, if I take a look at, let me see if I got one right here, and I want to monitor my tags. Let's see if I can find my SQ file. There we go. So here I am right here. So here's 10. And it's easy to type 10 in here, but if I wanted to go and come in there and say, all right, well, this is supposed to be, a 0 here, and this was supposed to be a 1 here. Oh, wait a minute, I missed a spot there. I wanted the 1 here, whatever. That's just a pain in the butt. But if I go and I want to change, quickly put in a number, once I know the number, I like to just go to decimal and type in 10, and then sure enough, I got my word, the binary word that I want, and that gets pushed out to my output module. So being able to quickly change from binary to decimal and then use that to manipulate the data in your program is critical. Okay, so that was that one. Moving on then, we had part 3 of this PLC right here. So a couple things that we needed to take into account is that you need a storage too. You need a preliminary device here, because when you take something in, you cannot directly take it on your sequencer. You cannot take your array in destination. You can't just push that baby right out to your module. And this, one of the things that you needed was a move, okay, to a storage 2, and then a storage 2 could have been your destination. So that's one kind of item that I warned you about, that sometimes if you can't get data to go with your instruction, do a little move into a temporary storage, and then take that new tag and then plug it into your command, and then it works, okay? And that's what was happening here. We couldn't have taken this local 5 data. We couldn't have put that right here. That didn't work. We had to do the TOD there. Part C, the SQI performs the task of an equal. So there's my SQI right here. And basically, this is just a big equal. So it was trying to take a value and either off of the thumb wheel or taking the value from the HMI, and it was comparing it to these numbers right here, okay? And how did you get this to come through? Well, you needed a sequencer here, an SQO, because when this came high to low, high to low, high to low, that's what advanced the position and length here, and it just kept going 0, 1, 2, 3, 4, 5, 6, all the way up to 8, and it started again 0 up to 8 really fast. And then because it used the same control, this position kept changing and this position kept changing, okay? So what did I do here? Basically, I put this on a timer, a really fast timer. Look at that preset. That thing is flying. So this is flying through the positions, just constantly running through these here, taking, there's 8 of them, taking 80 milliseconds. I could have made it faster to fly through here. And as soon as my source, storage 1 here, or something coming from the HMI or from the thumb wheel, was equal to one of these numbers, well, then you got the unlock light to come on. And the unlock light then broke the timer and it quit cycling. So that's how those two work together. Most people figured that out, and it worked pretty well. Part D. There's a couple of ways to do Part D. And what we had here, what we had going was a sequencer right here. We were running through a sequencer. And we were using a pulse timer here. Pulse, pulse, pulse. And what we did is, because it was like 34 seconds, each one of these got pulsed for 1 second. Okay, each one of these got pulsed for 1 second. And so this 10 right here, as I just showed you, meant that a certain light was on, and that light stayed on here, and it stayed on here. There wasn't any change in the lights here for the first, 16 seconds, whatever. And then something here, looks like a yellow light came on, and then a red light came on. And it just kind of ran through this sequence of lights here. And however long the light sequence was, you just had a different item pushed out there for that, okay? Another way that you could have done this, here's my data, by the way, so there's my 10, and if you look over here, that meant that apparently light 2 and 4 were on, light 2 and 4, okay? So that was what was happening for that, and you tied it into an HMI to make a nice item. The other way that you could have done this was you just could have had two sequencers. So the first sequencer right here did just what we wanted to. Here's the 10 again, so it pushed the 10 out. But what this is cool is the second sequencer here is the number of times that 10 gets pushed out. We put 16 in here for that timer, and so that timer times for 16, and then this sequencer advances to the new position 9, and the second sequencer advances the time, and so 9 gets pushed out for 4 seconds, and then 8 gets pushed out for 1 second, and 32 gets pushed out for 8 seconds, and then it'll go through there and it'll start over. So in this case, the sequencer does the data, but we only got to do it once because the other sequencer does the timer, and this is in your book, okay? And then so finally we had a move with mask to have the blinking lights. And so if you take a look at my program here, I can maybe pull it up here and maybe it'll look a little bit better. And so here's my move with masks right here. And basically the counter accumulation .0. So that basically goes, because it's a counter, 0 returns 0, 1 returns 1, 2 is 1, 0, so it goes off. Then 3 is 1, 1, so it goes on. So these are alternating back and forth because that 0 bit keeps alternating between 0 and 1. And what I do is I take my data here and I push it out to my local module, and I have a mask right here. This mask only lets those two lights get affected, okay? And there's my source, pushes that number out, and it masks them out. And the reason I do that is because up here, I'm using my output module right here. I've already used this data right here. And so down here, I'm pushing something out that's going to kind of overwrite this right here. But it doesn't matter what I push out right here because for the majority of this data, because my mask is 0, zero is on there. And so it's not going to overwrite the data that's being pushed out here. It's only got a couple of 1s in here on those locations, or a couple of that are the blinking lights. So those are the only ones that can get rewritten. Okay, so that's the way that my mask and my source is working here. I was pushing out different ones. Your traffic light might have had different data. So hopefully you understand how that move with masks works to only affect specific data that you want, okay? We're going to move on to our analog right here. And what we want to talk about is our current loop. So analog modules can be sourcing or sinking. This is right out of the book. And the voltage can be supplied by the sensor or the module. So this is some of this is similar to the way that we normally hook up our field devices, but these are going to have infinite values. It's not going to be on or off. It's going to have an infinite value. So the basic ones are voltage sensing or current sensing. So you might have like a 4 to 20 milliamp sensor, or you might have a 0 to 10 or negative 10 to 10 voltage sensor. So there's the two types of sensors. Each one has a little bit benefits and drawbacks. Okay. So typical analog inputs are 0 to 20 milliamps or 4 to 20 milliamps. That's what a sensor that you might want to see. That's a current rated sensor. Or you can have 0 to 10 volts. And so your analog input module can be set up and configured to read this. And this is a range, because you might have, it says 4 to 20, you might have 7.963 milliamps. And that means something. We'll have to do some scaling, or it might cut the voltage, all right? It accepts the analog signal and converts it to a digital signal. So we're going to take that analog in, and we got to make it into digital. We got to make it into zeros and ones so the PLC understands it. And the analog output module takes the digital signal that we end up with, zeros and ones, and then it punches it out and it converts it to, a number of 37.65 or whatever that we want as our output. So analog inputs and outputs. Okay. 5 quantities, for example, that are analog that you might find is temperature, because it's not off and on. It could be an infinite number of readings. Speed, like in your car, what's today's pressure, levels, weights, position of something. If you're on a linear slide and it's moving back and forth, well, there's how far down the track has it moved. So these are some quantities that are typically measured with analog, okay? The main element of an analog to digital converter is the analog to digital converter, and there's 2 different types. There's bipolar and unipolar. So whether we're going from negative 10 to plus 10, or if it's only unipolar, it's from 0 to 10. Same thing, a negative 5 to 5 or 0 to 5. So we would be working with the trainers in the classroom are 0 to 10 volts right there. That's what they're set up to read. They are unipolar. Okay. Resolution we talked about. It's the smallest change in input value that can be sensed. And so the smallest change that can be sensed, and we had some information that we did for the group homework handout right here. It showed you that if you had a 4-bit resolution, or an 8-bit or a 10-bit, or in our case, the cards were 16 or 32-bit. Remember that this is 4-bit gives you the range using binary, 0 to 15. And so if you take your full scale of 1 and divide it by the number of bits that you have in the resolution, that's basically chunking that up. So the more bits you have, 16 or 32, the more you can take 1 and divide it by that many, and that you get a much better resolution. So you get 0.00001. That can mean that little 1 can represent not very much. But if you don't have many bits, that 0001 in this case, because only 4 bits, boy, that 1 sure is a pretty big chunk here, okay? So this is going to be much better resolution. And here is an example of 4 bits using into 5 volts. So if you get 4 bits, and you can make all the combinations you want, 00001, go through and put 1s and 0s in here, and you're going to find that these are the combinations that you can make using, 1, 2, 3, 4 bits right there. Okay, those are all the combinations. You get 16 of them. Can't get any more. Good luck trying to find more. But if you take 5 and you divide it by 16, well, then that's what you get. You can 5 divided by 16 is a resolution of 0.33. So every bit that you get, it just increments by 0.333 all the way up to 5 volts. So that's how that worked. That was the group homework, and we'll take a look at it. Okay. Unlike voltage input signals, current signals are not as sensitive to noise. So if you're going to go and you want to wrap something in twisted pair, then you'll put a shield on it, and then you won't get quite as much noise. So that's why you're going to see a lot of 4 to 20 milliamp sensors. Okay, you're going to have a power supply here on the sensor versus this one is a module supplied power supply. So you'll have either one. That's a little bit different. Normally we would source and sync our modules for digital, but here you could actually have the sensor with a power supply on it. Okay. The main elements of an analog output module is the digital to analog, and it's varied by the control of the PLC program, and it controls something. So in this case, this valve right here is not on or off. There's a little motor on here that spins, and it kind of opens this valve up to allow a little bit more flow or a little bit less flow to come through. And that's not on or off. It's variable. So that's an example of an output. Okay. So in this case, the PLC controls the amount of fluid in the tank by a percentage of the valve that we open, 30, 40%, 36%, whatever. And we could even have a feedback loop here that's sensing what's going on and take that in as an input, and then we could adjust the output even more. Now see how that varies the input, and we could take it in and adjust the output. So this valve could constantly kind of be opening and closing to get the right flow and the right sensor and everything like that. Okay. So when we talk about analog numbers, we'll be using real numbers, okay, which is floating point. So when you go to set up an analog, it is going to be a floating point number, a real number, and that means it's going to have decimal places in it, and you can get any number that you want. Okay. Analog IO module, you're going to set this up. Points per channel, whether you want typically 4 or 8 points per channel. That's how many sensors are going to come in on the card. The current and the voltage ranges that it has, 0 to 10 or 4 to 20 or 0 to 20, those kind of things. And same with the output. So you'll be setting up those when you get an analog card that will match the equipment that you have. Okay. There's input protection. They're protected. They're internally fused and stuff like that, similar to what we've seen before, and they're shunted a little bit. Resolution, we talked about how accurate you want this to be, and you got to make some changes here that you can, if you have different type of cards, thermocouple cards or whatever, to change, to be sure that you calibrate it a little bit, I guess, to be sure that you're going to get the readings that you want, because your field devices match to what your card is good for. There's common mode rejection on this, and this is out of the book. Noise is picked up equally in parallel wires, so we have twisted pair, and we get a spike in it. Well, they're subtracted. These two are compared against each other, and they need to match, and that's the way that they get rid of noise, because when you subtract this, then you get the signal that you want. Okay, so there's the setup of the cards. And the lab pretty much tells you, how to go and set up. I'm going to come over here and I'm going to get an analog input card. It tells you what slot it needs to go in, disabled keying. It talked about the normal things here, but what you really want to get into here is your configuration, okay? Now, what we got here is different channels, so you always want to be sure that you're configuring the channel like it should be. And what this is it's taking a scaling of, let's say, 10 to minus 10, if that's what your card was, but it could have been, let's say 0 volts was the low side to 10, and we could be engineering it from 0 to let's do temperature. Let's say 32 degrees was freezing and 212 degrees was boiling. Okay, so if this card took in 0 volts, well, then it would know that it was 32 degrees. If it took in 1 volt, well, it's going to be more than 32. You can do the ratio here. It's going to be 18 degrees more, and we'll do that in a minute. It'd be 50 degrees, okay? But it also works if it's 6.673 volts, then it does it. So this does the conversion for you automatically based on the voltage that you're coming in, okay? There's some limits here that you can set high clamp and low clamp, and basically this tells you if you're exceeded the input voltage reading by so much, or if you've got below it. And you can use that. Here's my channel calibration range. These are the things that you use to set up whether you're using voltage or milliamps and get your card all the way set up. Okay, and the lab tells you how to go through and set those cards up. So we have a couple of scaling examples. So the analog trainers typically need some calibration, and you might not be able to get the voltage that you want, but when you get that voltage, it's always interesting to see exactly what you got going. So what we're going to do right now is we'll just take a look at a couple of scaling examples and be sure that that makes sense to you. So we'll come right here. And so the first one here, it says an analog pressure sensor is going to read pressure from 10 to 155 psi. So what I like to do is I like to kind of draw this on a little scale like this, and I'm going to put psi right here. Okay, and it's going to read here from 10, and it's going to read up here to, let's say, 155. So that's my psi. We're going to set up the module according to manufacturer, who says disregard voltage. So really, we want it to read between 1.5 and 8. That is what we want it to read. So at 1.5 VDC, this is my VDC right here, and this is 8 VDC. Okay, it says what is the PSI per volt. So if we get this, we're going to take the PSI equated to voltage. So on this side, you see that the PSI, our range here is 155 minus 10. So the difference here is 145 psi. Okay, so psi per volt. So we get 145 psi per volt, and our voltage range here is 8 minus 1.5. So it's 6.5 volts. So if we were all the way down here and we added, we'd be at 10 psi, and we added 6.5 volts up to 8. Well, we'd have to add up 145 psi. So there's a ratio here. And so what is it? 66.5 volts. If I come here and I go 145 divided by 6.5, I get 22.31 psi per volt. What I also want to do is I want to take the inverse of this for the heck of it. I'm going to take the 1 over the x right there, and when I flip it, I get 0.045, and that is volt for psi. Okay, so that just depends. Am I trying to do my psi per voltage, or am I converting voltage to the psi? So that's just the relationship, depending on if you're giving voltage and you want psi, or if you have psi and you want to get voltage. Those are the two ratios that you would use. Okay. And it says we are going to set the module. This is what is the voltage at 97 psi, right? Okay. Well. Let's take a look at it. So 97 is going to be, let's see, 9, yeah, it's kind of going to be kind of up here somewhere. There's 97. So how are we going to get 97? Okay, well, we know that we are going up from here to here. 97 minus 10, that's 87 psi. Okay? And so we're going from 1.5 up to some voltage level here, and we need to figure that. So we're going up 87 psi. What are we saying? It was 22.31 psi for every volt. So if we have to go up 87, it's like, yeah, it looks like it's about 4, doesn't it? Because the first voltage would get us up to, it looks like about 32. The next voltage would get us 32, 42, 52, 54. The third voltage is getting us up there. So what we need to do is we need to take how far we want to go, 87 psi, and divide it by 22.31 psi per volt. And if we do that, we get 87 divided by 22.31. We get 3.899. I'm just going to go 3.9. 3.9 volts. Okay. What does that mean? Well, that is how far we moved up the scale. But remember, we started at 1.5. So we need to add 3.9 volts onto 1.5. Just like we added 97, we went up 87 on top of 10. We go 3.9 on top of 1.5. So 3.9 plus 1.5 is 5.4 volts. So right here at 5.4 volts, we would be getting 97 psi. Okay? So it says, what is the equation of this line? So then what we're looking at is the equation of y equals mx plus b. So somewhere here, we went in 20s, 20, 40, 60, 80, 100, 120, 140, 160, 180. We'd have some scale here. And then if we were going up, we were going to go up to 8 psi. So we can probably just go with like 0, 1, 2, 3, 4, 5, 6, 7, 8. There's my voltage here. And here's my psi. So basically what we have is we have at 155 psi. So here's 140, 160. So it's maybe like in here somewhere. And we would have 8 volts. So come across here. So there's my first point. That's this point here, XY, okay? And at the other one, it was at 10 psi, which was here, kind of coming up. We were at 1.5 volts right here. So somehow there's a linear line that comes through here that we can get the equation of, okay? So what we can say is y equals mx plus b. And we can just pick one of these points right here. And if we want to get this point right here, we know that it was 1.5 VDC equals, because we're doing VDC, is equal to, let's get our number here, 0.045 volts per psi times x, because this is my y and this was my x. That was when it occurred at 10 psi. So basically I took y, which was this side right here, and plugged it right in, and x, which was this scale here, and plugged it in, because we knew that when it was 10, it was 1.5, and that's what we've got right there. When it was 10, it was 1.5 plus b. So I do this, I get 1.5 VDC equals, these cross out, 10 times 0.045 is 0.45 volts DC plus B. Subtract 0.45 VDC from each side, and I get 1.05 VDC, something like that. Okay, it's pretty rough there. And that equals B. So my equation of the line is y equals 0.045 volts per psi plus 1.05 V volts. Okay. What does that mean? If I were to take any one of these x's right here and plug it into here and solved it, it would return me the number on this side, that y right there. Okay? And so to take any of these numbers here and plug it in, and you'll get the answer here, and you'll be right on this line right here. That's the equation of this line. Now, this is kind of complicated to do. You think, like, that's pretty crazy. But that's the beauty of the software, okay? So when you come to the logics right here, and you look at the analog input card, and you do the configuration, and you set your scaling, like we were doing there we were doing, low signal was 1.5, and the high value was 8, and we said it was equaling 10 psi up to, we said 155 psi. Well, the computer just did all that for you, okay? And so you don't have to necessarily do that math. You need to understand this math, because when you get some readings or when you go below this scale, you got some things you need to think about. For example, if it goes to 1.3 volts, yikes, you got some problems there, okay? So, if I go back to here, I think I have another scaling example that I want to take a look at. Let me see. It says what happens when it goes to 1.3 volts DC, okay? So if I go to here, that's where it says right here on the next page. If the sensor reads 1.3 VDC below the recommended read, what is the pressure? Okay, so now we've got a problem right here, okay? So what we've got going is the value has got below the curve here, and it's got below here, so we're looking at 1.3 VDC, right? So, you know, then what is going on here to get this value right here, okay? So the way that we can solve this, because we're outside the range of the engineering on the card, and it's not going to give us the answer, okay? So what now we can do is we can use our formula right here to solve for what that would be. So we've got y, and our y in this case is what we're reading here for 1.3. So I'm going to take this, I'm going to go 1.3 VDC equals 0.045 volts per psi times x, and that is what we're trying to solve, right? Plus 1.05 volts, okay? So what am I going to do? I would come over here and I would take this minus 1.05. So 1.3 minus 1.05 is going to leave me 0.25 VDC is equal to 0.045 volts per psi times x. And then what will I do? I'll come in here and I'll take 0.25 and I'll have to divide each side by 0.045. So 0.25 divided by 0.045 equals 5.55. 5.55, and they cross out. Volts is equal to x. So let's take a look at that. Does that make sense? If we go lower here, it comes at 5.55 volts. It says it's lower. And so that's the way that we solve this, because the engineering that I showed you on the PLC is only addressing this range. When we go lower, we have a problem here, and that we would have a hard time going back and getting this value right here, okay, when it goes lower than that. Okay, let's see what else we got here for you. So we did the scaling data there, where you might have to extrapolate some data. You might have to go lower than what it is talking about, okay? We also had, that was a scaling example 1. I actually did a little bit out of order. They're complicated. We can go ahead and take a look at the scaling example 2. Perhaps this one was maybe a little bit easier to look at. But an analog temperature sensor is reading from 0 to 212. I'm going to go ahead and make this 32 to 212. Maybe it makes a little bit more sense. And that's what we were talking about before, okay? And so what we had was Fahrenheit and voltage. So at 212 to 32, it was scaled to read 0 to 10 volts. Well, this seems pretty easy, doesn't it? The range here between these, if you subtract them, is 180 degrees. And the range between here, if you just subtract them, is just 10. So it looks like if I divide 180 by 10, I get 18. So basically that's saying that's 18 degrees per volt, volt. So if I went up 1 volt right here, 18 degrees, 32 plus 18 is 50. If I go up another degree. I got to add 18 more, 58, or excuse me, 68, etc. And then it would just go all the way up there and it would match up nice, right? And then if we wanted to do Celsius, it says, what is the card reading for Celsius when it reads 6.8? Well, fortunately for Celsius, at 32, it's 0 degrees, and at 2112, it's 100 degrees, okay? So if the card was reading 6.8, here it is right here, 6.8 volts. Well, this is just a factor of 100, so you're going to say, hey, it's reading 68 degrees Celsius. And you could certainly multiply this 6.8 times 18 degrees per volt, 18 degrees per volt, right? These cancel. So 6.8 times 18. 6.8 times 18 plus the initial 32, because we started at 32, plus 32. So that's 154 degrees, 154.4 degrees. So these are all just equally ratioed here. The ratio of 212 to 10 and 32 to 0. Remember, that's what the PLC can do for you. And then the voltage is just pretty easily ratioed here. It looks like it's just 10 to 1. Now, this falls apart, as I showed you last, when you don't have nice fancy increments to divide here. Or if we change this voltage to, let's say it was going to be 4 volts to 10. Ooh, now that's ugly, because we have to 10 minus 4 is 6, and then this side needs to get divided by 6. 180 needs to get divided by 6 instead of 10, and then this side is now messed up because it's a range of 100 that needs divided by 6, and all these ratios change a little bit, okay? So you just want to be aware and understand the math of how the computer is ratioing all these, especially when I come and I say, hey, at 20 degrees Fahrenheit, what's the voltage? Now that it all falls apart all of a sudden, and then you have to go back and you have to get the slope of the line so that you can work backwards from the set point and down from the set point to get to where you want to be. Okay. Let's see what else we got here. So, add-on instruction. In this one, you're going to be setting up an add-on instruction, and I'm looking here, and this is not the lab that I have it set up. An add-on instruction is an instruction that's similar to a function block, okay? And so when you create an add-on instruction, it is going to then populate here under add-ons or my favorites, whatever you call your add-on instruction. I think our one is called F to C here, our first one that will convert Fahrenheit to Celsius. It will populate right here, okay, F to C, and it'll be on my favorites, okay? And so how does that work? Well, the add-on instruction for Fahrenheit to Celsius conversion basically looks like a function block, and on this side we have Fahrenheit coming in, and on this side we have Celsius coming out. So what's going on in here? Well, inside of here there's some logic, and it's going to be to convert Fahrenheit to Celsius, or Celsius to Fahrenheit, you're multiplying or dividing by 5/9, and subtracting and you're adding 32, and that's that little formula, okay? And this is the ladder logic that will be put in here, and then this will have a command, a thing called F to C, and you won't be able to see the logic there. You can click it and see the logic, but it's just going to come on as an add-on instruction, so that whenever you put in this, it'll automatically generate that. You can make much more complicated add-on instructions, and we're doing one called scale with parameters, okay? And in here, what we're going to do is we're basically going to do that engineering and that math that we talked about. And so a minute ago, I showed you an example where we were taking in 32 degrees and 212 degrees, let's say, and then we wanted it to come out as 0 to 10 volts. Okay, so this took my two ranges, and basically, like we did, we subtracted this, and then we subtracted this, and then we divided it, and then we took whatever number we wanted then, let's say it was 154 degrees or whatever, and then we multiplied this by the subtraction and the ratio of all these, and then basically what it kicked out, because these were voltage here, it kicked out the voltage here, which, you know, I'm looking here, it's probably going to be about 6.3 volts or something, okay? But all that math occurred in here, and this is like a little function block, and when you go ahead and you create that function block, then or an add-on instruction, then you'll see that it then exists up here as a command that you can then use forever and forever, okay? So that is the gist of the lecture this week, and we'll take a look at the lab.